after our Strut-and-Tie, after we developed STM-CAP, we wanted to check the accuracy, like how accurate is the program working, like if there is any issue or anything. So we checked it with another available software, CAST. It works also on the same principle. It is developed at University of Illinois. So for the verification purposes, what we did is we selected bridge Pier caps and we modeled the bridge Pier caps in STM-CAP, and we found a state of utilization ratio. And what we did is like we modeled the same bridge Pier cap in CAST also to find utilization ratio. And in CAST we found pretty much exact, or you can say like almost the same utilization ratio. We did this process for 8 bridge Pier caps and we found very accurate result. In some of the cases there were like slight discrepancy. We verified it using hand calculations, and what we found is like hand calculations showed STM-CAP results are more better. Then we also checked this with non-linear finite element analysis. My colleague Anish will carry over.
Thank you. So we develop a program that's which depends on Strut-and-Tie method, but AASHTO recommends us to use either Strut-and-Tie method or nonlinear finite element analysis for these type of members. So in this section, we model the same bridge Pier's cap using nonlinear finite element analysis, and we compare. We see how conservative Strut-and-Tie model is than nonlinear finite element method. For this purpose, we choose a software called Vector2. Vector2 models two-dimensional. Vector2 create two-dimensional finite element model, and this program is based on modified compression field theory. AASHTO also is based on use modified compression field theory, and this program models concrete that is smear rotating crack. And there are many second-order material properties that are considered in Vector2, like compression, softening, tension, splitting, tension, stiffening. So we can expect a much higher capacity and lower utilization ratio if we perform the study from nonlinear finite element analysis using Vector2. So we choose a cap beam that was already studied using the software STM-CAP, and you can see the geometry of the cap beam that we use. These are taken from the engineering drawing, and we create a model in Vector2. This one is the model that was generated from Vector2, and you can see the different colors shown here, and this different color shows the different shear reinforcement in different region of the Pier cap. This model was run until the failure, so that we can see what's the stress in the concrete and reinforcement at the failure. So from nonlinear finite element analysis, we generate the stress distribution in the concrete and the reinforcement. We want to see how conservative the results were with the Strut-and-Tie. So we convert those stress distribution into a same number called utilization ratio. So here we determine the utilization ratio from the stress distribution that we get from nonlinear finite element analysis. First, we generate the stress distribution at the failure load. You can see that's the stress distribution of the concrete. You can see the red color, which represents the strut action. Then the critical regions were marked in the stress distribution plot. You can see the red circle that shows the critical regions in the concrete, and the same regions that were marked in the failure load were marked in the factor load. These were the zone from where the crack or any failure in the concrete can occur. So we mark this region first, and we mark the same region for the factor load. Then the average stress inside that region was calculated, and which was divided by the capacity of the concrete to get the utilization ratio. So in this way, we find the utilization ratio for the concrete. We follow the similar procedure to find the utilization ratio for the reinforcement also, but unlike concrete, where failure start over a region, in reinforcement, failure start from the single point. So we find that critical single element from our stress distribution of the reinforcement, and follow the similar procedure to get our utilization ratio. So in the figure, you can see that was the top rebar region, and the arrow shows the most critical element in the stress distribution of the reinforcement, and you find the utilization ratio for that point. Next, we compare the utilization ratio that we get from our solution algorithm with the nonlinear finite analysis, and you can see this is the most critical region, which is the A2 from both the method. The utilization ratio in that region was maximum from both of the method. Black one shows the result from the Strut-and-Tie, and the red one shows the result from the nonlinear finite element analysis. The reason with the maximum utilization ratio from the Strut-and-Tie was same as in the nonlinear finite element analysis, and the reason which are very low utilization ratio from the Strut-and-Tie have a low utilization ratio from nonlinear finite element analysis. So from here, we found that the behavior that was captured from our program was similar to the one that we get from the nonlinear finite element analysis. And also the governing member was same. And we found that this utilization ratio that we found from the methodology that I described before shows that these utilization ratios were 40% on average of STM of Strut-and-Tie. And this was expected since we are considering many second order material properties from our nonlinear study. So we get more capacity from nonlinear finite element analysis. We performed this test in 5 more bridges with different shear span to depth ratio, and this was the result that we plot between the utilization ratio and the shear span to depth ratio. The green one shows the result from nonlinear finite analysis, and the capacity calculated were much higher than Strut-and-Tie method. And however, the modeling time and the analysis time that was required for the nonlinear finite element analysis was significantly higher. For a single Pier cap, it took like more than 2 days to do this calculation, whereas from STM, you can do that in less than an hour.
All right, thank you very much, Anish. So, sectional method, as I mentioned, it's not appropriate for deep members. It's good for using it in slender members, but just to see the discrepancies in the predictions, we also ran all the database. These are existing bridges located in Columbus area, some of them Dayton area. And we analyzed them using both STM-CAP Strut-and-Tie method as well as the sectional method. So for the sectional method, we determined some critical locations. In this example, this is just I'm showing one of them only, A, B, C, D. And then we created the utilization ratios. The smaller the utilization ratio, the more capacity you have. And if you look at the ratios, in this case, it's 2.5 times larger utilization ratio. So if you analyze section AA using the sectional method, you would find that it fails much earlier than Strut-and-Tie method. And I'll show you a global plot in the next slide. So this is my favorite plot because this really pretty much summarizes all the verifications in a very compact manner. If you look at the horizontal axis, this is shear span to depth ratio, right? And I mentioned that if it's less than 2, it's deep. If it's larger than 2, it's slender, right? The vertical axis shows utilization ratio. 1 represents it's at the capacity. So you don't want this to be high because larger than 1, it's overloaded. So let's just compare STM-CAP with nonlinear. As expected, definitely nonlinear analysis will give you more capacity because there are lots of behaviors considered. There is stress distribution. STM-CAP will stop analyzing if a rebar yields, but we know that after yielding, a lot of things will take place. Because the yielding is at the very beginning of the response of a rebar, and then it's going to go into strain hardening, and it's going to go into rupture phase. So nonlinear finite element considers all of these, and it's going to give you the best and most accurate prediction. That's for sure, and it's really consistent, around 0.2 utilization ratio for the beams we analyzed. This is not generalized. This is the database that we looked. And on the other hand, if you look at the sectional method, which is the red one, see they are converging at around span to depth ratio 3. So I would assume if larger than 3, sectional method would be very good. But if the beam gets deeper and deeper and deeper, the discrepancy will be bigger and bigger. So in this case, you see you are going to get 3 times more capacity when using the nonlinear method. If you look at the Strut-and-Tie STM-CAP, it is definitely gets closer to the finite element as the beam gets deeper, So as you can see, the accuracy following the blue line, and it converges to the sectional method if span to depth ratio of 3. I would easily say that, you know, up to 3, it would be appropriate to use the sectional Strut-and-Tie method. Larger than 3, you can use sectional method for this, for our database as it's shown.